Okay, so far in our Waves Toolbox, we actually have 5 equations, okay? I'm just going to go over them really quick again. The first one is a basic definition of frequency. Frequency is how quickly you shake something, how often a wave occurs. It's measured in hertz, and it's the reciprocal of the period, which is the time for one cycle, okay? So like a hummingbird, okay? You guys ever see a hummingbird before? It's really cool. Like, you usually see them in California, but I just took my kids to the Morton Arboretum yesterday because it was nice out. And there was actually a hummingbird there. I'm like, cool. Like, we actually have these in Illinois. I didn't know that. A hummingbird is like little tiny bird, and it flaps its wings around 80 times a second. So what's the frequency? It's 80 hertz. And it's cool because it's faster than what the human eye can see. It just looks like a blur. And so the hummingbird, because its wing frequency is so high, it can actually float like a helicopter in place. It can drift backwards, up, down, sideways, and all that. And hummingbirds usually fly from tree to tree and like flower to flower because they drink nectar or something like that, right? Okay? And if I wanted to find then the time for just one cycle, one flap, it's just what? 1/80th of a second, right? And that's what period is, okay? When you tune your radio dial, it's all measured in what? It's measured in hertz, thank you. So when you tune into like WHSD, what's our school radio station again? 88.5. Yeah, I actually don't get it out where I live because some students were like, listen to my show, Mr. Lau, and I'm like, I just get static, okay? But what it is it's 88.5 megahertz, million times per second. The electron in our school's radio antenna, which I think is right on top of the building, okay, is shaking the electrons that many times per second. Next, we have our wave velocity equation. This is a biggie. We use this all the time, okay? The only thing that's weird about this is this little funny-looking Greek letter. Okay, what's this Greek letter again? This is the Greek letter what? Lambda, okay? When I was in college and I'm doing all my physics homework, some of my problems were really nasty. It would take like 2 to 3 whole pages of just trying to solve it. And I remember I was in a speech class, and this girl leaned over, and she's like, cool, is that Chinese? And I'm like, no, it's actually Greek. It's my physics homework, okay? Because we just have to use Greek symbols after a while. We run out of letters, okay? Velocity, wave speed, is equal to wavelength, the distance it takes the wave to repeat itself, times the frequency. So if you think about it, if you multiply wavelength in meters and then frequency in hertz, which is cycles per second, you get meters per second. You take the distance a wave travels in one cycle and how many cycles it makes every second, you'll get how far it goes, okay? There's also the basic speed equals distance over time, but we express it as v equals delta x over t, where delta just means change in your position. The fourth one isn't really a formal equation. We don't really use it very much, other than these are some basic facts, okay? The speed of sound in air at room temperature is about 340 meters per second. Technically, I think it's 343 if you use 20 degrees Celsius, or you could calculate it using 331.5 plus 0.6 t. We don't really use that one very much, but it's just good to see that. If you know the temperature of the air, you could theoretically find the ideal speed for how fast sound travels through the air. And then for light and radio waves, we'll get into this more in our next unit, it's the ultimate limiting factor, 300 million meters per second, or 186,000 miles every second, or 7.5 times around the Earth in a second, okay? Then equation 5 is the sound energy equation. The intensity of sound in watts per square meter is just the power of the sound divided by 4 pi r squared, which is the equation for the what? The surface area of a sphere. And if you think about it, like if you clap your hands, yeah, the sound waves travel out like ripples in a pond, but in 3D. So all you do is you just need to know the energy of the source, the power rating, and then how far away you are, okay? So in terms of plugging and chugging, you just shove in numbers, but the big idea you want to see from that equation is it's an exponential relationship. So I'm all into, in this unit, like trying to see the big picture. And the big picture I want you to get out of this in terms of real life, like 10 years from now, you won't really remember like you grade on a physics test, but here's one thing I do want you to remember is don't trash your hearing, right? And if you want to be 10 times, let's say you want to sit in the first row at a rock concert, and you're 10 times closer than your friend who's 10 rows back, is the energy 10 times more going into your ears? No, it's 100 because it's r squared. You see that? So you're actually trashing your ears like 100 times more, right? If you're 100 times closer, what's 100 squared? Like 10,000, right? Okay? Next, I'm going to add in a couple more equations. This isn't really an equation, but it's a relationship. I'll just label this as number 6, okay? And that is on the decibel scale, okay? There's that weird equation that the book uses. We're not going to use it because we're just going to do it conceptually, okay? For every 10 decibels you go up on the decibel scale, remember how much louder it sounds to the human ear? It only sounds what? How much louder? Twice as loud, but it's actually how much more intensity or energy. It's actually 10 times the energy or intensity, yeah? So why is this practical? Well, suppose like your mom likes to listen to music at 50 decibels, okay? But you're a crazy teenager, and you listen to it at 70 decibels. So how many more decibels is that? That's what? 20 decibels more. How much louder does it actually sound? It actually only sounds 4 times louder, okay? 70 decibels compared to 50, but it's how much more energy? Careful, right? What's 10 times 10? Aha, it's 100 times the energy, okay? So you're actually destroying your hearing 100 times more, okay? And for a lot of you guys, it's about 85 decibels is what research shows where you start to suffer long-term hearing loss. And a lot of you guys, because, MTV generation, iPods and all that, you're way above 85 decibels, okay? So do yourself a favor. If you are using your headphones, because it pumps the sound energy right into your ear canal, just turn it down a little bit, okay? And then when you do like it loud, blast it on your stereo and stand a little bit further back and jump up and down, okay? And then turn it down so you can still hear it. What if we're 30 decibels more? What would be next in the pattern? It'd be what? 2 times 2 times 2 is what? 8, right? Which is how much more energy? 1,000, etc. Okay? What would be next in the pattern? I'm not going to write it, but it'd be what? 40 decibels would be what? 16 times or what? 10,000 times the energy, okay? Another way to look at this is roughly, okay? And it's because we're not doing the main math. 3 decibels is about twice the energy, okay? But it's not twice the loudness. In fact, your ear can't really distinguish 3 decibels in terms of being that much louder, okay? Because you have to go 10 decibels higher, 10 times the energy before you actually hear it being double the loudness. So 6 decibels would be roughly how much more energy? Roughly. It'd be what? 4 times the energy and so on and so forth. Okay? Finally, the last kind of mathy stuff is we had what's called music, right? And on a musical scale, okay? And I tried to do a little bit more research on like sharps and flats and why the book uses that, 24, 25th. And actually, I don't know where they got the number from, so I'm going to email the company because I saw some other weird ratios, like 128 over 125ths or whatever for alternate methods of tuning. But what's the best way to tune using the equally tempered scale? What's that magic number? You guys remember? D, 2 to the 1/12th power, the 12th root of 2, right? Do, re, mi, fa, sol, la, si, do. That was painful, okay? A full octave, what happens at a full octave? It's equal to what? 2 times the what? The frequency, right? Yeah, no problem there, okay? So in other words, if I tell you that a C is 256 hertz, do, okay, a C4, what would a C5 be? Do, painful. If it was 256, it'd be what? Just double that, right? 512 hertz, yeah? And then how do I go from one note to the other one? What's the magic number? I've been calling it magic, but the formal name is, it's called the semitone ratio. And what's that magic number? It's just the, what? 12th root of 2, right? Or 2 to the 1/12th power, yeah? Is another way to look at that. This is how you put it into your calculator, 2 to the 1/12th power. Because if you think about it, to go from one note to the next, okay? If you want to double your frequency in 12 steps, to go from a C to a C, okay, a full octave, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 steps there. Okay? And so what's nice is by having all of these equations in one place, you're not focusing on memorizing, you're focusing on application, okay? Whether it's solving problems on your homework or for tests, or like 3 weeks from now, okay, when we study light and you want to look up like, what is the wave velocity equation? You have it all in one place. And for final exams, it's a great study tool. In college, a lot of professors probably won't let you use a note card on exams, but again, it's a great study tool. Because usually, once you make it, you own it. You know the material there, okay? And the goal is having all the tools for success. Kind of like a carpenter, you got to have your tool belt to, build the deck. You need your hammer and your screwdriver and all that. These are the tools for your brain, okay?